It's great to see you again. So how about last week is visiting high-speed computer center? Is everything good? Wonderful. Okay. So we are not intend to have a lot of lessons on the computer design and simulation because this course's focus is not on that. But it's good to give you some experience and understanding what kind of resource you can have. In the future, if you are going to do the simulation, you can use the resource in a high-speed computer center. Okay. So now I am going to move on to the next topic. So the next topic is an important topic because it's a real design for accelerometer by using the CMOS process. Okay. So in the past couple of weeks, I have been through many different kind of fundamental things, including how to do the fabrication and how to what kind of a CMOS process you have. And now we are going to use all the knowledge together, so to do a real design, okay, of an accelerometer. So we are going to move on to the lecture 7-1, the Moses scan design example. We first give the first example on the piezoresistive type accelerometer. Okay, so I think you have been seeing these pictures for many times. Okay, so now I'm going to give you a little more detail about what's the meaning and the structure of this kind of design. Okay, so currently we are going to use a CMOS process to design a accelerometer. The accelerometer will consider a proof mass, so you can see this top view and also the cross section. Okay, and the cross section is here. So from the top view, for accelerometer consists a proof mass and a cantilever beam to connect to the proof mass and to the base. And the dash area corresponding to the area we want to open to the etching process. So at the end of the CMOS process, we are going to take away all the material under the proof mass and also the cantilever beam. Okay, so the whole structure will be released and as a beam suspended above the surface. So that means the black one, the black part, the proof mass, this part can move up and down freely according to the acceleration, okay, from outside. So we can use this as a sensor. However, in order to use this as a sensor, you need to measure what kind of a movement it has. Okay, it has. For example, like a move up and down, how far away, okay, and also what kind of the distance, deflection. So in this case, we are going to put the sensors. You can see the sensors on the side of cantilever beam. So these two sensors we will talk about a little more later. It's a piezoresistive sensor. The piezoresistive sensor is kind of a resistance sensor. So when we have like a strain, stress applied onto the beam, the cantilever beam, so you will see the deflection of the beam, not only the deflection of the beam, but also the deflection will generate some stress or strain on the surface of the beam. So if we put the sensors on the top, the sensor will be stretched, either stretched or compressed. So in that case, the length of the sensor will change, and also the resistance of the sensor will change as well. So we measure the resistance change, we can understand how much strain which has been given onto the sensor. And also from the sensor, we can get a signal, like a voltage signal, and we can have the measurement. So that's the basic idea. So this is a whole structure we are going to design. Okay, consider proof mass here, cantilever beam here, and also sensors here. So the sensor is not only a single sensor. You can see the sensor pair. I will talk about it a bit more later. Why do we need a pair of sensors instead of only one sensor? And also, it's a kind of a bridge. It's a circuit bridge. It's not only single sensor over here. So we need to do comparison between the sensing part and also the reference part, and then get a signal. As you can remember in the previous homework, we designed a current mirror, right? And the current mirror will go through two resistance, right? In your previous homework. You are going to give me the homework result, right, today? Okay, great. So, so any kind of a sensor design, system design, usually you have one pair of sensors. That means you have one reference. The other one is a sensing. So you always compare the sensor signal from the reference signal. Yeah, see the differences. Okay, so the design here is similar. Okay, but the difference is that we have a sensor pair instead of only single sensor. So this is the top view. Okay, so on the bottom you have see the cross section. It's kind of blow up of the cross section. Actually, the cross section is pretty thin. Okay, as you can remember, the thickness on the proof mass are only like 6 micron. Okay, it's not very thick. And the cantilever part, remember, consists of 4 layers of a major oxide layer, silicon oxide layer. So the thickness is around like 3 point something micron. And on the side, this side, the cross section, if you have a cross section across the sensor part, not only the silicon dioxide cantilever beam you can see here, but also it consists of 1 layer of the sensor layer. So the sensor layer here we are going to use polysilicon, poly 1. The poly 1 thickness is only 0.4 micron. Okay, so this sensor will be embedded inside the cantilever beam. Okay, so on the sensor top we have a protection layer, and on the bottom we also have protection layer as well. So the sensor is embedded, 埋在里面, inside cantilever beam, with some kind of distance to the center of the cantilever beam. So this is the fundamental design of this kind of sensor. So so when we are talking about a mass accelerometer, so we are talking about need to consider proof mass, just as mentioned here, proof mass, and the force detection system. Here is a force detection system. We are currently using the piezoresistive type sensor. We will talk about this later. And how to release the structure, because the structure needs to move up and down. Okay, later on, when the acceleration or the force go into interact with the sensor. So the bottom part of the sensor need to be taken away. The material need to be taken away. Consider we have teach you about how to remove all the materials under the structure, the cantilever structure, by using bulk machining. Okay, because of corner attack and also the some kind of a micro machining process, you can take out all the material under the cantilever beam part, and also the proof mass part. So to release the structure. And the detection method currently is in piezoresistive. Actually, there are many different kind of types. You can use in capacitive type, inductor type, using tunneling effect. A lot of different kind of methods you can apply. So here I will just show you the most simple one. Okay, by using piezoresistive. So it consists only a resistor here. The resistor will change its resistance according to the strength applied onto the cantilever beam. Okay. So this is the rough idea of the design. So now we go to the second part. So when we have acceleration, the signal, how can this signal to transfer according to this structure of the device into the final signal for detection? Apparently, when you have acceleration, the acceleration gives you some force. And the force need to using some kind of method to detect. Otherwise, you don't know how large the force is. So, so now we consider the structure here. So the input is acceleration. The final output will be, we want to transfer the acceleration into the final product. Our final product is the voltage change. So through many different stages. So I put all the stages here for you to preview. Okay. Actually, each step, I will give you very detailed formulation and also the calculation process. So you will end up, you will understand why we will coming out to the final results. Okay. So starting from acceleration, finally we want to get the voltage output. Okay. So that's why how the sensor workful. Okay. So now we come back to the original one. So starting from the acceleration, coming to the sensor. So what will be the action of the sensor? So consider there's a cantilever beam and also proof mass suspend at the end of the cantilever beam. So when we have an acceleration going to the cantilever system, the proof mass here will encounter one acceleration. So the acceleration will generate a force. The force we call is a virtual force. Is a proof mass, the mass times the acceleration. Okay, so mass times acceleration, that means it's a force. Okay, you will encounter a force. So this action is similar when you standing on a bus. When the bus starts to move, you feel your body go backward. Okay, that kind of backward force is a virtual force. It's similar to this one, inertial force. Okay, so the amount of inertial force is your mass times the acceleration you encountered. Okay, so first the cantilever system encounter a force. The force is driven by giving acceleration. So the force amount is the mass m times the acceleration a. So when the cantilever have this kind of force generated onto the cantilever beam, the tip, okay, so we will have a deflection of the beam. So the deflection will be proportional to the moment, okay, generated on the beam. So the moment, the bending moment, will be the force times the arm, the length of the arm, okay. So the force is ma. The length of the arm will be the length of the cantilever plus half the length of the proof mass. So the length of the cantilever will be LB. LB means the beam, the length of the beam, okay, cantilever beam, and the plus half of the length of the proof mass. The length of the proof mass is LP. Okay, we using P to consider as a plate. Okay, it's more like a plate. Okay, so the total bending moment will be the force times the length of the arm, the total arm. Okay, so once you have the bending moment, so the beam will start to bend. Okay, so when the beam start to bend, so the top surface and the bottom surface of the cantilever beam will feel differently. So when you have a beam bending down like this, the top surface will feel like stretched, right? The bottom beam will feel like compressed, the bottom one. The beam top and the bottom will feel differently, okay? So if you put a sensor on the top, either on the top or on the bottom, you can sense the stretching or the compression of the beam by measuring the strain. Strain means the diffraction, the variation of the length corresponding to the original length. So you have a displacement, not displacement, you have distortion, you have the length change on the top surface and the bottom surface. This can be measured by your sensor, the strain sensor. So the bending moment through the bending beam, the beam bending, that will give a stress on the top and the bottom. The stress will also generate some strain. That means that the structure change, the distance change, the distortion. So these are kind of a change. We call the stress. Okay, will be proportional to the bending moment you give onto the beam. So you have a larger bending moment, you give a more diffraction of the beam, and the more strain or more stress will be generated on the top surface or bottom surface of the beam. Okay. So once you have a stress, we need a special mechanism to change the stress into the resistance change. So by using the piezo resistors, the piezo resistor actually is a kind of resistor. The resistor is sensitive to the change of strain because you change the structure, the length of structure. The resistivity or the resistance is changed accordingly. So the stress change, in this case, will be transferred by using the sensor. It's a piezoresistor is a sensor. Transfer into the resistance change. So once you got a resistance change, the resistance change can be easily read out by using a circuit, okay? So the Wheaton bridge is kind of circuit. You put the resistor inside the Wheaton bridge. When you provide some voltage across the bridge, you will see the voltage change according to the resistance change, okay? So this is the final result you have, okay? Because the voltage is, differentiation is quite small, so actually we need another circuit to magnify the signal. So usually we're using the electronic amplifier, either OP amplifier or different amplifier to amplify the signal by 10 times, even 1,000 times, in order to give us a large signal to read out. So this is the whole process. So starting from the beginning, the acceleration, we review it again. From the acceleration, we change into the bending moment. The bending moment bend down the beam. The bending moment will generate stress on the top surface or bottom surface of the beam. The stress can be further transferred into resistance change by using piezo resistors. So the final change of the resistance can be further transferred into voltage change. So at the end, we measure the voltage change and get the final results. So as you can see, if we have a larger acceleration, we can have more bending of the beam. If we have more bending of the beam, we can have larger stress or strength generated on the top or bottom surface. Then we can have a larger resistance change and the voltage change as well. Okay, so that's why we can use this mechanism to do the detection of acceleration. So this is a whole system, we call it the accelerometer. Okay, so during the signal transformation, actually there are three inputs of the noise from different aspects. So the first one, actually, we call the mechanical noise. So the mechanical noise will appear when you have a proof mass and also cantilever system. So the outside interference, like a vibration, like some kind of you have an inside atmosphere. So the molecule, the gas molecule, will keep bumping onto your cantilever. So those things will give the mechanical noise. So this is the first stage, you got the noise. The second stage you got the noise is from the resistor. Because the resistor is a transport electrons inside the resistor. So when you have you are using the resistor inside atmosphere, so it's kind of elevated temperature. So in elevated temperature, the electrons when they are moving inside the resistor, they will encounter a lot of resistance and also some kind of interference according to different temperature. So this will give another source of we call the resistive type of noise or Johnson noise in the second stage. In the final stage, because you are using electronic circuit to amplify the signal, so there are also some electronic noises. Okay, we call it like a frequent noise or sharp noise. Those different kind of noise will go into the circuit to bring you some background noise as well. So these three different kind of noises will have a different strength and also different magnitude, and they come in from different origin. So the final noise will be the combination of those noises together. So that's why it's important to reduce the noise in order to have your signal to noise ratio large enough for detection. No matter how sensitive your sensor is, if you got a lot of background noise, if the signal is smaller than your noise, so the whole system cannot do good detection. Okay, so it's important. We need to understand the noise resources and also try to reduce as much as possible the noise during the detection. So in order to get a good signal to noise ratio. Okay, that's our goal. So this is also part of the design, actually. I said not only we want to bring up the signal as large as possible, but also want to reduce the noise at the same time. So the final purpose will be generate a good signal to noise ratio sensor. It's not only to increase the sensing part, but also reduce the noise part. Okay? So now you have an overview, but don't worry about each equation. Actually, I will go to the detail to develop all the equations one by one for you. So you will understand them in detail. So here, this map is important because this map will give you a rough view, okay, for you to understand the process of signal transferation and also how to generate good signals later on, okay? If you have some different ideas, you can come back here and to try to see which part you can improve more. Okay, so after understand the signal process flow, then we go to the dynamics, okay, of the sensor. The sensor is like a accelerometer is for detection acceleration. So the sensor will consider three important parts. The first one is the proof mass. This is kind of model, okay? So the model drawing is a little bit different from our previous cantilever, but the idea is the same, okay? So the first one is the mass, okay? The second one will be a spring, okay? This one is corresponding to spring. And also damping, okay? And then on the bottom, we have the sensor. Number 5, let's see, number 5 is the, number 5, this is a damper, the spring, damper, and on top here is the sensor, okay? So we split the three important parts into three devices here: mass, spring, and the damper. And then also the sensor here to measure the displacement. So consider this a big box here. So when we have acceleration encounter with this big box, the outside box will have will feel acceleration in one direction, and the small box inside will feel the acceleration in the other direction. Okay, opposite direction. So when the mass field acceleration, actually the distance between the large mass and the small mass would be different. For example, you move the large box upward, the small proof mass inside will go downward. Feel moving downward. So the distance between the small mass and the large case will change, okay? So in this case, the spring here will extend, okay, become longer. And the damper here will feel some force press onto the damper, okay? So the distance change can be measured by the sensor here. So that's the basic idea, how an accelerometer works. Okay, so now we go to the dynamic equation. So we consider this is a force balance condition. That means when you give some force, the acceleration into the system will feel the force from the inertia change, the distance change. So this change will corresponding to the inertial force. That means the acceleration means we're using x represent the position of the small proof mass, and the big X corresponding to the position of a large case. Okay, X means a proof mass, small mass. X means a large case, large mass. Okay, so you will feel the first one, the acceleration of the small mass. The acceleration times the proof mass, the small mass, you will find out the inertial force which has been generated onto the small mass, which is nd squared x dt squared. Okay, the second derivation. Okay, you got the acceleration. And then we think of the differences of the small mass and the large mass, there's a displacement between them, okay? The distance change. So the distance change is not a static situation. It's a dynamic situation. That means there's a acceleration between them. So that means not only a distance change, but there's also a corresponding speed between them. Okay, a speed, the moving speed. So the moving speed will be the first derivation of the distance. So the relative distance variation, or the relative speed, will be d small x dt minus d large x dt. And the damping is usually proportional to the speed, okay? The moving speed between these two mass. Okay, consider damping is like a friction things, okay? The friction things usually try to diminish, try to decrease your energy, the total energy in your system. For example, you have a block moving on the ground, okay? So the friction is always have opposite direction, give the opposite direction of the force to your moving direction. So the friction, usually the purpose is to try to reduce the total energy in your system. For example, the kinetic energy, the dynamic energy in your system. So when you move a little bit distance, the block will start to stop because the consumption of all the energy from the friction. Okay, so damping is similar to friction. So damping is usually the action to reduce your total energy, to consume away your energy. It's similar to friction. Okay, so the force, the damping force, is proportional to the speed. Okay, the relative speed between your large mass and small mass. So when the small mass try to move down toward the cast, okay, so the damping force will try to squeeze to push the full mass upward, so in the opposite direction. So the damping force usually operates in the opposite direction. Okay. So that means this part gives you a negative force. If this part gives you a positive force, the second part gives a negative force. Okay. Yeah, because a large x move a longer distance and the small x move a shorter distance. So the difference between them is a negative. You can see a negative speed here. So this is a negative force. Okay. Then in this case, because the large case move up, the full mass move down. So the spring here will extend. Okay. So the spring force will be the difference of the displacement of the spring, the distortion of the spring, times the spring constant. So this will give the spring force. So the spring force will be also small x mass large x. So all these three forces will be balanced. Okay, inertial force, the bending force, and also the damping force. So the acceleration is related to the second derivative of the distance. The damping force were related to the speed. Okay, so this is the first derivative of the position. And the spring force will be proportional directly to the displacement. Okay, to the change of the length of the spring itself. So these three forces come together will be balanced, equal to 0. Okay. So this is an equation of the instrument, the dynamic equation. So you can see it's a second derivative equation. So it can be solved. So now we're using another parameter we call z to replace the distance difference, the position difference, large x minus small x. So the whole equation can be rewritten into the second one. Okay, the second one will be using z as the major parameter. the major variable for the whole system. And because in the first term, there is no large x, so in order to make this become a z, so we need to add another 1. So that means on the right-hand side, we have added one more term over here, the large s term, in order to make the left-hand side into the complete z term over here. Okay? So now you find out that it's become a final equation. So the z means the relative displacement between the large s, small x, and the large x. So so you see this small mass from when you are sitting down onto the large mass and look into the small mass to see the relative displacement and also the dynamic situation all the time. Okay. So this dynamic process will be balanced with the acceleration. So the acceleration from the large mass. Okay. When the large mass encounters acceleration from outside, the acceleration will give some dynamic action onto the system. The system means the small mass plus the large system, the relative distance change, okay, will be according to the outside input of the acceleration.